Welcome to The Explainer. Today we are diving deep into the absolute cornerstone of modern technology, the transistor. We're going to explore how this one tiny component can have three totally different personalities, and how just changing up its connections unlocks a whole new set of powers.
So I want you to think for a second. What's that one tiny, microscopic component that acts like a brain cell, but for our electronics? There are literally billions of them inside our phones and computers, powering our entire world.
You've got it. It's the transistor. And at its heart, it's pretty simple. It's a tiny little device that has two amazing superpowers. First, it can be a super fast on-off switch, and that's the basis for all the ones and zeros that run our digital lives. And second, it can be an amplifier, taking a really weak signal and boosting it up into something strong and useful.
Okay, so how does one little thing do all that? Well, a transistor has three connection points. We call them the emitter, the base, and the collector. And here's where the real magic comes in. Depending on how you wire those 3 points up, the transistor's whole personality changes. So let's break down the 3 main ways you can connect one.
First up, we have what's called the common base configuration. Now, the name gives it away, right? The base terminal is the common ground point that the input and the output both share. You feed the signal into the emitter, and you take the output from the collector. Simple as that.
Next, we've got the common emitter configuration. Now, this one is by far the most popular, the most widely used of the 3. This time, the emitter is our common point. We put our input signal into the base, and we get our output from the collector. This configuration, you'll see, is an absolute workhorse when it comes to amplification.
And rounding out our trio is the common collector configuration. You can probably guess this one. The collector is the common terminal. Your input goes into the base, but this time, the output comes from the emitter. This setup has some really interesting and unique properties that we're going to get to in just a bit.
So we know the 3 different ways to hook them up. Now let's talk more about that amplification superpower. To really understand how good each configuration is at amplifying, we need a way to measure it. And we do that with something called the current amplification factor, or what most people just call current gain.
The idea here is actually really easy. It's just a simple ratio. How much current do you get on the output compared to how much you put into the input? That's it. A bigger number means more amplification. And each of our 3 configurations has its own special name for this gain factor.
So for that first setup, common base, the gain is called alpha. It's the ratio of the output current from the collector to the input current at the emitter. But here's the really weird part. Alpha is always less than 1. Wait, less than 1? How is that amplification? Well, it means this setup doesn't actually amplify current. It seems kind of strange, but that very property makes it super useful for other jobs, like in high-frequency circuits.
Now let's look at our most popular setup, the common emitter. Its gain is called beta, and this is where the amplification magic really happens. Beta is the ratio of the collector current to the tiny little base current, and its value is usually really high. We're talking around 100, maybe even more. It means a tiny trickle of current at the base can control a massive flood of current at the collector. And finally, for our common collector configuration, the gain is called gamma. This is the ratio of the emitter current to the base current. And just like beta, gamma's value is also nice and high, which means it gives you a serious amount of current gain. Okay, so we've got these 3 different gain factors, right? Alpha, beta, and gamma. Now, they might seem like totally separate things for 3 separate circuits, but the truth is actually so much more elegant. They are all deeply mathematically connected.
And it all starts with this one simple, fundamental rule of transistors. The current that flows out of the emitter is just the sum of the currents flowing into the base and the collector. Think of it like water pipes. What flows in has to flow out. Every relationship we're about to see comes from this one simple truth.
So here's our first big connection. This formula shows us that you can figure out that huge current gain, beta, just by knowing alpha. And remember how alpha is always a number just under 1, like 0.99? Well, when you do 1 minus 0.99, you get a tiny, tiny number. And dividing by a tiny number is what gives beta its huge value. It just goes to show how sensitive everything is. And of course, the math works in reverse too. If you look at a data sheet and you see that beta is, say, 100, you can use this formula to find alpha. You get 100 divided by 101, which is, about 0.99, a value really, really close to 1, just like we said. It all fits together perfectly.
Now this relationship is my favorite because it's just so simple and clean. The connection between gamma and beta is that gamma is always just 1 more than beta. That's it.
So if beta is 100, gamma is 101. They're practically joined at the hip.
And this last formula beautifully closes the loop, showing a direct link between gamma and alpha. So what's the big takeaway from all this math? It's that these three values, alpha, beta, and gamma, aren't independent at all. If you know just one of them, you can always figure out the other two. They're just different lenses for looking at the same transistor. So the big question is, why does any of this matter? Why do we even need three different ways to do this? Well, it's because each configuration has this unique blend of characteristics that makes it the absolute perfect tool for a specific job. Let's put them side by side and see what I mean.
Okay, let's walk through this. Look at common base. It's got very low input resistance, no real current gain, but a high voltage gain. That combo makes it perfect for high-frequency circuits. Now, common emitter, our all-star. It gives you high current gain and high voltage gain. That's why it's the go-to choice for things like amplifying audio signals. And finally, common collector. It has a super high input resistance, but its voltage gain is basically just 1. It doesn't amplify voltage at all. So what on earth is it for? It is a master of something called impedance matching. You can think of it like an electronic diplomat, helping a circuit with high resistance talk to one with low resistance without any signal getting lost. It's a crucial middleman.
All right, so to wrap it all up, the transistor is our fundamental building block, our electronic brain cell. How we connect it, common base, common emitter, or common collector, completely changes what it does. Each has its own current gain, alpha, beta, or gamma, and all three are just different views of the same thing. At the end of the day, we pick the right configuration for the right job.
And that kind of leaves you with a pretty cool thought, doesn't it? It's just amazing that by simply changing three little connections, you can get such a wild variety of behaviors from one component. It really makes you wonder, what other simple components are out there, just waiting for us to find the right connection to unlock their hidden superpowers?